Okay, thank you very much. It's going to be a little different. It's not going to be quantum mechanics, but it's going to be more technology meets the morning speakers. Okay. So, and this is not my own area of research. It's more, I got involved with this through public policy with OSA, the Optical Society, now known as Optica. Because we in optics like to say it's the technology for the 21st century, and it's public policy because we want to convince every government of that. And it just happened that in 2015, almost every government signed on to the Paris Accord. So we thought this is a good thing to explain to all governments. And so this is how we got into using optics to look at the environmental measurement and monitoring. So as we already heard this morning, it's not just measuring CO2 in the atmosphere. All of the various spheres are combined, and that if we really want great climate models, we need to understand all of it, right? I mean, the atmosphere warms up, and so the ocean warms up, and the ocean's rising because of the cryosphere melting, and we've already heard we need the biosphere to live. And so, and maybe the one that we have the least impact on is geosphere, except when we maybe are fracking. But we still need to know when volcanoes go off, because that will also affect our atmosphere. So it's an awful lot to know. And on the other one, you could go back to Lord Kelvin, who did say, when you can measure what you are speaking about and express it in numbers, you know something about it. But when you cannot measure it and when you cannot express it in numbers, your knowledge is of a meager and unsatisfactory kind. Now, I was then disappointed this morning when Francine said she had the numbers, and still her scientific colleagues didn't think that was enough. So I don't know what to say about that. But for most of us scientists, we think as long as we can put numbers to it, it tells the story. So that's what the optics people are going to bring to it. Oh, this is not the top. Anyways, optics is typically what we see with our eyes. That was the way it was defined. But we optics people don't like to be that confined, so I will tell you that those of us in optics will take everything from the X-rays through the infrared and now call that optics, okay? Okay, and the other reason that we think it's so useful is the fact that no matter how light interacts with whatever material, it can change in so many ways. The simplest one is the fact that it would just change the direction, but we can also change the color, which is spectroscopy. We can also change the polarization. Is the electric field in a plane? Is it a circle? Is it elliptical? And it will change upon interaction. And the other one that's easily measured is the change in the power or the intensity of the light through its interaction. And because light changes in all these ways, depending on what it's interacting with, then it can tell us a lot about the environment by these measurements. So again, because we have to take so many measurements, we're going to want to keep it as inexpensive as possible. Some of the things that we're going to want to do is just find a leak, and so we're not going to use the most sophisticated one for that. And so this is when we use LiDAR, which is just like radar, except that both is Mie scattering, and Mie scattering is the type of scattering that happens if the object is about the same size as the wavelength. So if you're talking about radio waves that are a meter size, this is why radar is used for telling us our car is speeding, or it was done in the military so we could find military objects. Whereas now we're talking about the environment, and a lot of talk was about aerosols this time. So it's not going to be looking for molecules, but it would be looking for aerosols or particle sizes on the order of a micron. And so we can just see how many particles there are in the line of sight, and we can scan the laser around and see what the size of the object is. So this is something very simple we can do to even find if there is something like a leak in a gas line. So because I'm from Canada, I'm going to show Canadian examples here because they help me put the slides together. So Institut National d'Optique, and it's not the Canadian nation, that's the nation of Quebec, has this Optics Institute. They're working with different companies, and they've come up with an ultraviolet, a spectroscopic LiDAR. So once you find it, they can also know what the objects are made out of by using spectroscopy. Ultraviolet means that you could even find smaller particles because the wavelength is smaller. And I usually show this slide just to show that there are numbers on this slide, so that we are putting numbers to it. Also, what they're trying to show is that it's inexpensive, and I'll get to that later, but you can see it's a small object until you turn around and see that there's also an entire trailer full of instrumentation that goes with the small LiDAR instrument. So again, the big part of doing optics, though, is spectroscopy. Different people call different things the molecular fingerprint, but this one is for the greenhouse gases, so that if you have some kind of light source that can span the 2 to 5 micron range, if you can do it with good spectral resolution, you can determine which of the gases that you're looking at. And as this was already shown this morning, but of course this has been going on since at least 1960, when we were looking for CO2, and we've watched the CO2 grow alarmingly fast in the last 40 years, or 60 years, I guess. And so that's one of the common examples, but it's not the only thing that we now measure with spectroscopy. So now this is from the National Research Council in Canada. This slide is really showing that we can now take tunable diode lasers. We can make the whole spectroscopy system quite small, so they can either fit on a small drone for maybe agricultural monitoring. They're also quite proud that they got it onto this Mars mission to look for methane. I have no idea why we need to know if methane is on Mars, but apparently we do. And so they were able to do that. And so this gets us to the GEMM network. So this is something that Optica is working with AGU on. So Optica is one of the world's large optics associations, and AGU is one of the world's large ones to look at space and Earth science. And the idea is that in order to speed up these measurements, because we still want more measurements, there's still some disagreement with the satellite images down and the ground-based instruments. To have great climate modeling, we want to have all these many measurements. We also want the government policy people at the table. We want industry both to, once researchers come up with the new technology, to make sure the technology is there, but industry there also means we want the polluters also at the table, seeing what's going on. International standards, we can't have numbers unless our measurements are really accurate. So we want all of these people at the table at the same time, so that we can keep feeding each other, so that we have the best climate modeling and the best methods to detect everything. So this is an example. University of Laval in Quebec, I think, took this idea before we had it in Optica. And I will give a shout out to my colleagues in Laval. About a decade ago, Canada started this big granting thing, and Laval said, what we're really good at this university is optics, which I knew about, and Arctic biology, which I did not know they were good at. And this university said, we will let both of your areas go for these big grants, but we don't want you just to both go for your own grants. You must try to work together. And then we will put all of our eggs into these 2 baskets and go after just these 2 types of work, but you must work together. And so Sentinel North was created out of that, and they got 2 circs in Arctic biology and now 2 in optics. And so just to understand this, which I can't point to, what this is showing you is one spot on the Earth. This is the Green Edge Ice Camp, which is in northern Canada. And so it's time of the year going from left to right. So on the left side, you see winter, and you'll see that whether it's a polar bear or a person, or you think it's a seal, hopefully not all at the same time, standing in that one spot on the Earth, they're standing on just over 1 meter of ice. This research that's trying to be done is to understand the spring bloom of the phytoplankton, which is being changed because of climate change. And so you can see on the far right side is July, summertime, and the ice is gone. And now the ice starts melting in mid-May. And apparently then, as soon as the ice starts to melt and makes holes, then the sun can get through, and that's what starts the algae, and that starts the whole process to grow the spring bloom of the phytoplankton. So, which is important for our biosphere and is affected by both the temperature of the air and the temperature of the ocean. The point of this slide, though, is to show you, to make this one environmental measurement of the spring bloom of the phytoplankton on one spot on the Earth requires this many measurements. The ones that are circled are the photonics ones. There are other measurements there as well. But this really highlights why we need GEMM networks around, is that in order to really understand either the adaptation or just, fixing climate change, we're going to need to make so many measurements, we would like a lot of these versions of Sentinel North around the world. Oh, another one then, and it was already mentioned, the permafrost. This is getting to be a real problem for the people in the Canadian North because they only actually can travel on land in the winter there where they're on ice roads. In the summertime, they count on everything coming to them by plane. But because the permafrost is no longer permanent, the runways are buckling. On the other hand, our optics people at Laval, many of them had been working in optical communications because that was so strong until the early 2000s, and then they had a pivot. And so they've pivoted to doing fiber optics as sensors, and they're putting these fiber optic sensors both in the roadways and in the airplane tarmacs to see what's happening with the permafrost not being permanent. I'm not going to do that one. Okay, so now what's the advantage of being part of a global network? Tom Baer, who really got this whole thing started, talked to Professor Cohen at the University of Berkeley. And he's come up with what he calls low-cost sensors. These are 10,000 US dollars, so not everybody calls that low cost, and I'll come to that. But he has set them up on this grid all over the San Francisco Bay Area on a 2-kilometer grid so that he can observe on a continuous basis what's going on with all these various greenhouse gases and the 2 particle sizes. So Tom Baer also has connections then at the University of Strathclyde, and so he suggested that they do the same thing in their sort of Bay Area. And the thing that I liked about this when I first heard about it is they've put each of them on top of schools in Glasgow. And so it's also a great citizen science project because the students are getting to see what's happening at their schools. And the one person who was from the public policy of Glasgow said at the one meeting they thought this was going to change public policy and make parents not be allowed to drive their kids to school anymore because they saw the pollution going up at the beginning and end of each day. So then I was giving this talk at StarMist this year, and so I asked if they actually made that public policy change, and the scientists said no. In the end, that policy did not get actually changed. But at least the students know that by being driven to school, they are causing pollution at their schools. Now back to it being a network, the Berkeley group has come up with this transport model, and so they can determine where the various pollution is coming from to that one detector. Of course, you can only do it if you have a network of detectors, but they can decide why that one detector is measuring it. And then this is also then being compared to the Glasgow measurements so that they can have 2 different groups taking the same measurements and making sure that they both get the same accurate results and improve their transport model. So that's why we would like to see a larger and larger network around the world. I think I'll miss that one too. Oh, this was my talk for another, I don't know how I got this in. Doesn't matter, I'm gonna end here. So this is the network as it stands right now. I will say that I've been trying to get a Canadian-wide network going in Canada, and that's why there's a gray one in Alberta, if any of you know Canada. But I'm the one that's sort of with the Great Lakes all around it. That's Waterloo, and we just started our network, and we just signed the MOU with Optica, and we're gonna have our kickoff meeting on October 2nd. And we're gonna try at Waterloo. We have an Institute for Climate Change, we have a Water Institute, and we have an Institute for Nanotechnology, and I see GEMM as the bridge of those 3 networks to bring the people together to see if we can hasten some of these measurements. During COVID, we did try to get a meeting going, and one of the examples of how this works is that one of the chemistry professors said, I've got this new micron size widget that will go into the Great Lakes and can measure fluorine. And the environmental scientist said, well, that's really great that you could measure fluorine, but we would rather you be able to measure the difference between chromium-3 and chromium-6, because one's okay for you and one's not okay for you. And so then when I asked him to speak at this one, I said, did you ever try that. And he goes, yeah, I've already published the paper. I've already got it out there. And I said, did you go back to the environmental scientist who asked for it? And he goes, no, I forgot who asked. So we're hoping that that same environmental scientist also shows up and we can let them know they now have their sensor built. That's the point of bringing these two disparate groups of people together. Can we get more and more measurements for the environmental scientists, and can we find more and more applications for the optical people? And I'll finish just with the cost. I gave a version of this talk when I was inducted into the National Academy of Sciences in the United States, and there was a mathematician that heard the talk and said, oh, my friend is a biologist in Madagascar. So you'll see there is a gray one in Madagascar there. And they really wanted to set up these detectors. Because of the way the farming is done, in the fall there is a lot of black smoke in Madagascar. Unfortunately, the $10,000 per detector, although that's called inexpensive to Berkeley, it's not inexpensive to Madagascar. So we are still trying to find ways to help fund this thing. So those are the various ones that we're either in talks with, or the colored ones are the ones that have already gotten started. They look at water, they look at air, they look at different things. And that's it. I really just want to give a shout out to Tom Baer, who made many of the slides, and those other people made the other slides. And thank you very much.